This video has been produced by Crown Cork and Seal in conjunction with CMB Engineering Seaming Systems to promote customer training and the correct procedure for setup and evaluation of double seams for food cans. In this video, you will see the process of double seaming, how to evaluate seam quality, with an introduction to operating and critical parameters. In addition, we will discuss key steps required to target set a seamer and the operating and process limits necessary to ensure good double seam quality. As the can is fed into the seamer, it passes a sensor. This activates the no can, no end arrest finger, which allows an end to be fed by the magazine into the guides via a feed screw. The end is transferred by a turret onto the can at the make-up point. The first operation roll moves in and rolls the end curl under the can flange to form the first operation seam. Just after the peak of the first operation cam, the first operation roll moves away and the second operation roll moves in. The second operation roll moves in to compress and complete the seam, thus forming a hermetic seal. After the peak of the second operation cam, the second operation roll moves away, the lifter descends, the can exits the machine via the discharge turret. Seam evaluation should always be carried out on consecutive cans from numbered heads, each head being treated as an individual machine. Two categories of parameters characterize a double seam: the operating parameters and the critical parameters. The critical parameters are those that define the integrity of the double seam. The operating parameters are countersink, seam height, seam thickness, body hook, end hook, and free space. Countersink. This is where the seaming chuck locates and supports the end. Seam height is the overall outside measurement of the seam. Seam thickness. Nominal seam thickness is 3 end thicknesses added to 2 body thicknesses, plus the free space, which is the allowance for the compound. Body hook is formed from the flange of the can. End hook is produced from the curl of the end. Free space is calculated by deducting the 5 material thicknesses from the seam thickness. It is normally around 5.5 thousandths of an inch, or 0.14 millimeters. Sometimes free space is included as a critical parameter. The operating parameters should be within the tolerances on the specification sheet to ensure all the critical parameters are acceptable. Critical parameters are tightness rating, actual overlap, and body hook butting. Tightness rating refers to the amount of ironed out end hook below the worst wrinkle, expressed as a percentage of the end hook length. Actual overlap is the amount the body hook overlaps the end hook. This dimension can be measured on sections or calculated on manual teardown. Body hook butting is the length of the body hook relative to the internal seam height. On teardown, it is calculated from seam and hook dimensions. It is expressed as a percentage to indicate the amount by which the body hook is embedded into the lining compound. Body hook butting indicates the quality at the primary seal area. Actual overlap and tightness rating indicate the quality at the secondary sealing area. For the finished seam, consecutive head-numbered cans are collected. Care must be taken to ensure can and head numbers correspond. Often this can be done automatically. Mark a minimum of 2 positions on the seam, ensuring subsequent checks will be taken at these points. For 2-piece cans, these 2 points are at any position around the can, but diametrically opposed on the seam. For 3-piece cans, the seam should be marked at the 10 o'clock and 2 o'clock positions, calling the can side seam the 12 o'clock position. Visual inspection for defects should be carried out. Rotate the can whilst looking for any defects, both on the external seam and internally in the countersink area. Seam bumps and seam springback can be identified from this visual inspection. All seams should be free from visual defects, as well as meeting the critical parameters, if the seam is to be considered safe. A damaged chuck will cause a mark or a lump on the inside of the countersink wall. Damage to the can flange may cause a knockdown flange or false seam. Seam bumps or sprung seams that could have been caused by over-tightening of second operation roll. Cutover is sharpness at the top edge of the countersink wall. These are just a few of the many defects that could be present. Any type of visual defects require further investigation. Before measuring, the gauges should be calibrated using the setting pieces provided. The external dimensions, countersink depth and seam thickness, have to be measured first using the appropriate gauges. As mentioned previously, the seam thickness depends on the combined material thickness. The component suppliers provide the body thickness for two-piece cans, but individual measurements must be taken for all end thicknesses and for three-piece body thickness. Now, the can is sectioned with a saw at the marked positions. This will allow for the internal dimensions to be measured with a projector. With an appropriate tool, push the sectioned part of the seam into the can, exposing the cross-section to be measured. If it is necessary, clean the exposed cross-section with an eraser. The saw blades must be replaced regularly to ensure a clean cut. The can should be placed on the projector and positioned to give the sharpest possible image for measurement. The section appearing on the screen will include measurement lines, which should be checked for position and manually moved as necessary. The seam dimensions can then be automatically recorded. To evaluate the tightness rating, it is necessary to tear the cans down. Remove the top of each can with an appropriate seam cutter or by hand. To determine the tightness rating, the end hook should be removed and carefully inspected for any signs of wrinkle. Wrinkle will have both length and amplitude and should not be confused with compound wrinkle that is caused by the impression of the compound onto the end hook. After finding the worst wrinkle around the hook, tightness rating is the wrinkle-free portion of the end expressed as a percentage of the overall end hook length. Seam results must satisfy critical parameters in line with agreed national standards. Actual overlap and tightness rating are critical, but different standards also include body hook butting and free space, as shown on the quality control chart. Seam dimensions are set out in the double seam specification for the particular can and ends being used and should be provided by the component supplier. Filling and processing should be carried out in compliance with the seaming codes of practice, such as the FDA and USDA. All cans should be free of visual defects. Any double seam defects found should be corrected by taking suitable action as suggested on this defects chart. Seam construction is interactive and single machine adjustments can alter several measured parameters. Seaming machines must be kept in a good mechanical condition to enable double seams to be consistently produced to specification. It is recommended that the seamer should have at least one annual audit and overhaul as required. Intermediate checks of machine timings, etc. should be carried out depending upon the machine usage. During initial setup, first ensure all of the seaming chucks are at a similar height, within 0.005 of an inch or 0.125 millimeters. Next, set the base loads to a target figure. Loads depend upon the machine type and components being used. The lifter height should then be set relative to the infeed table wear plate. Ensure that all the lifters are below the infeed table by at least 0.008 of an inch or 0.2 millimeters, depending on seamer type and running speed. Now set the machine pin height at the peak of the first operation seaming cam. Recommended pin heights are found on the specification sheets. The final adjustment should be in an upward direction to eliminate any backlash in the elevating mechanism. First operation seam setting is done at the peak of the first operation seaming cam. It is quite common to set seaming roll clearances with the use of a feeler gauge. With experience, the correct feeler can often give the correct seam thickness. First operation roll height should be set with the use of a gauge. This is put in position between the seaming chuck and the lifter, and then adjusted to deflect the lifter. This eliminates any lift that may be present in the seaming chuck, especially if the machine is in a worn state. The roll is adjusted down to lightly contact the chuck and then raised typically 0.03 of an inch or 0.075 millimeters to give the correct setup clearance. At least 3 cans are produced off each head and the first operation seams checked for seam thickness, seam height and countersink depth. Adjustment is made if any head mean is not within the setup limits on the specification. Second operation seaming rolls are set on the peak of the second operation cam, again using an appropriate feeler. However, the height clearance this time is set to 0.06 of an inch or 0.15 millimeters. At least 3 cans are then produced off each head, and the second operation seams checked for defects and against all parameters. Again, if the results for any head are outside the setup limits, adjustment is made until all heads comply. When each head and the machine mean are all within setup limits, production can start. There may be a difference between hot and cold results. During production, 1 can from each head should be checked for visual defects every 30 minutes, and a full seam check every 4 hours. Cans must be marked relative to individual seaming heads and taken directly after seaming, as processing may affect the double seam results. Mean results from 2 or 3 measurements on each can are compared with published operating limits. Individual results are also examined to ensure they are within the process limits. When any mean result falls out of operating limits, a further set of 3 cans minimum should be taken from any affected seaming head and rechecked against setup limits. If critical parameters are not met, corrective action must be taken. If other parameters are not met, investigation into the reason why should be carried out as soon as possible. Trends of critical and non-critical parameters are recorded to determine the process capability, and this also gives a good indication of progressive machine or tooling wear. Many seam faults form in the first operation, so it is important to check first operation dimensions at least once a week for first operation countersink, first operation seam height, and first operation seam thickness. For further assistance, please contact Crown Cork and Seal Corporate Technologies, Carno Metal Box Engineering Seaming Systems, Crown Food Can Americas, Crown Food Europe.